Welcome back to part 3, where I continue to make this fin assembly, and this is the full aluminum version. And this video will go over making the fins. So a lot has happened since the last video. Some highlights include being part of the team from the Washington Aerospace Club that flew the most powerful amateur rocket in Washington State to date. This was Project Moonliner, a 22-foot tall, 530-pound rocket that successfully flew on an experimental O7911. It was really awesome to be part of this team and contribute to this project. Event. Yes. Yes. I made massive fins for my friend Bryce Chains, and this is for his rocket named Q-Min. This is a sub-minimum rocket that will fly on a Q motor with a target altitude of 50 kilometers, so halfway to space. This was a challenging milling operation due to the size of the fins, but I learned a ton and I'm really happy to contribute to his project. I'll have a separate video on this whole milling operation in the future. Then I attended Balls 33, which is the largest experimental rocket launch event in the US, where I successfully flew Project Rosefire. This was the first flight of the full aluminum fin assembly that I will cover in the next couple of videos. Project Rosefire is a 3-inch minimum diameter rocket that flew on an experimental L1423, and it set a new Tripoli Research Group altitude record for the 75mm under 26-inch class, reaching 17,146 feet. But I get ahead of myself. Let's dive into how I made this aluminum fin assembly. In part 1 and 2, I made the forged carbon fin assembly, which turned out to not be as structurally sound as I hoped. This is why I embarked on making this fin assembly entirely out of aluminum. And at the time, I really hoped that using aluminum and the precision of the CNC mill would result in the strength and specifically the stiffness I was looking for. After 2 flights, I now know that this is indeed the case. The aluminum version does provide all the stiffness I was looking for. And when I refer to the stiffness, then it directly translates to having very little or zero movement between the fin and the bracket interface, since we do not want our fins to move or flex. Both tip movement and fin flex will result in a type of flutter, and that could lead to failure during high-speed flights. Before we start going over toolpaths and cutting metal, I wanted to give a brief overview of this specific design and why I chose it. It is a 4-fin design that is traditionally slightly harder to make, since there are just more fins to make and more fins to align. And honestly, I just like the look of a 4-fin rocket, so here we are. In hindsight, machining a 3-fin modular assembly is still possible, so this might be a future option. The fin aspect ratio is 9:1, so it has a 9-inch chord. It has a 3-inch span and a 1-inch tip with a sweep angle of around 69 degrees, making this a clipped delta design. And the leading and trailing edge bevels run from the quarter chord to the quarter tip locations. Head over to my website for more in-depth theory on the quarter chord principle, as well as the 50% chord and mean aerodynamic chord as it relates to fin design theory for sub and supersonic flights. Using OpenRocket, I ran simulations on various aspect ratio combinations, where I altered these ratios either independently or together, and in the end the 9:1 ratio turned out to be the sweet spot as it relates to maximum altitude, velocity Mach number, and rocket stability. So, a quick disclaimer, at this point in time I'm very much a novice machinist, So for all the experts and real machinists out there, I welcome the feedback and any help that you can provide. So now that we reviewed design, we can go over the machining setups and toolpaths. Making the fins on a 3-axis mill will require 2 operations since the fin has 2 sides. Machining the first side and then flipping the remaining stock to machine side 2. Milling the second side is the tricky operation since there is no easy way to securely hold the remaining stock in a vise while cutting the profile or outside edges to liberate the fin from the stock. Let's start with looking at the setup for the first side or operation 1. I like to define my stock as a solid object, so I model the stock relative to the part I'm making. I then reference this solid object in the machining setup. Then defining the work coordinate system, and I use a stock box point. I know this is not ideal and I should really be referencing a fixed point on the mill such as a point on a vise. I will do this in the future, so for now I'm just going to roll with this method. So onto the toolpaths for Op 1, and this is a high level overview and I'm not going to review all the magic sauce. Starting with a facing operation using a 2-inch fly cutter just for a cleanup cut. Onto the initial roughing operations, removing the excess stock to expose the fin contour and surface profile. Next I drill and bore the holes, and after that I cut the outside contour but only the bottom and trailing fin edges, and I also cut tabs to prepare for operation 2. So effectively creating a secure way to hold the fin in place for that operation. Onto the finishing operations, where I profile the fin surfaces with a ball end mill using a combination of flow and scallop toolpaths with a 20,000 step over. And I finally cut a reference pocket. This might be controversial since there's likely a better way to do this, but I really need to be able to reference a precise machined surface that was machined during Op 1 for Op 2's work coordinate system. As in, I need to be able to reference machined XY surfaces for Op 2. And this will likely make more sense once I show the setup for Op 2. I'm not going to show lengthy CNC milling operations. I could, but honestly recording inside the mill enclosure with flat cooling is nearly impossible. I do have mist cooling, but I still feel that flat cooling gives a better result. So I'm going to show the results after each cut or operation. Starting with the raw stock and then finding XYZ0. Then we're on to the first cutting operation, which is the face cut, and I'm taking 10 power just as a cleanup. I recently trammed my spindle and I'm currently trammed at 0, giving a super smooth surface finish. Next is the first roughing cut, exposing the fin profile. Op 3 exposes the rough fin surface profile, and you can see the fin starting to take shape. Then I drill and bore the holes for the mounting barrel nuts. With operation 5, I cut the fin cord and trailing edge, and as mentioned earlier, this is where I cut the tabs to assist with the future work holding. Operation 6 is where the magic happens, with a 1/4 inch ball end mill, and this is where I fully shape the surface profile. And here's a time lapse compressing the full 30-minute operation into one. and the end result looks pretty great. The 20th step over I used on that shaping operation really paying off. And then finally cutting that reference pocket for setup 2. So this is what we have after the first cutting operation. As you can see, half the fin is trapped in the remaining stock. I can clamp this in the vise and finish the fin surfaces since the fin is secured with the edge tabs. However, the problem is the final contour cut. The fin is floating in mid-air at this point, and if I was to remove the tabs with the mill and cut the final contour, then that'll just end badly. So the fin needs to be secured to something solid below to prevent disaster. This is where the mirrored surface plate comes in. It has to be a mirrored plate since the first side of the fin already has the aerodynamic profiles. The mirror plate will ensure full contact between the fin surface and this work holding plate. I will then super glue the fin onto this mirror plate to ensure a really strong work holding setup. And I use powder coat tape as a barrier to protect the surface from the super glue, and also makes the cleanup afterwards a lot easier, and technically makes separating the two sections also a lot easier. Starting with the machining setup, the stock is defined from the previous setup, and I use continue rest machining. Then things get a little funky as it relates to defining the work coordinate system and specifically the z-axis. So I create a sketch that uses the reference square from op1 to define the x-y axis intersection. So easy. For z, I also want to reference a machined surface, but at this point all machined surfaces are hidden. I cannot really reference a stock surface since that is not reliable. In the end, it is really just a game of relative coordinates. So I opt to use a flat surface on the mirror work holding base that I know will be in direct flat contact with the corresponding surface from op1. Then I create a sketch in this flat surface plane, and this will define my z-axis reference, or z0. Then the work coordinate system origin for op2 can now be set to this xyz intersection. Alright, so the toolpaths for op2. Let's start with roughing out the fin surface profile. Here I use a 3D adaptive toolpath for this initial roughing, and then I finish out the known flat area to final dimensions. Then it's on to finishing the surface using a ball end mill, using the same combination of flow and scallop toolpaths. Finally, I liberate the fin from the stock using a 2D contour operation, but before I run this, I add screws to further secure the fin to the mirror base. Again, I'm just showing the results after each milling operation. Here I'm starting with finding Z0 using the flat surface on the mirror plate. and then using that reference pocket to find X and Y0. The result after the first roughing operation, where the second side surface profile is exposed. The second milling operation uses a 1/4 inch ball end mill to fully form the surface profiles. Then adding the bolts to fully secure the fin before the last contour operation. The final operation cuts away the tabs and finishes the contour. And finally, liberating the fin from the remaining stock. This is what we are left with. The remaining stock can be removed, and then it's just a matter of separating the fin from the base. Start by removing the bolts. Then we add some acetone to kind of dissolve the super glue. Adding some heat just to kind of speed up this process. And then finally just some light tapping to fully liberate the fin from the base. And you can see how well the powder coat tape works to protect the surfaces from the glue, and how easy it is to clean up. It's just a matter of peeling away the tape. So what about the dimensional accuracy? I was shooting for 1/4 inch root thickness, and the final dimension is only 2/1000 of an inch over, so that's pretty great. So here it is, the aluminum fin in its final state. Now it's just a matter of repeating all these milling operations to make 3 more fins. The reality is that I've already done that, since you've seen this fin assembly in its final state. Onto the brackets. Follow along in the next video where I go over the end-to-end process of making the brackets, from the design to the manufacturing. And if you are interested in owning one of these fin assemblies, head over to my website where I'll have more information on timing and availability. And as always, thanks for watching.